Again, welcome everyone to Beyond the Equation. This is our second episode from our podcast that we provide over here from the physics department. We call it Beyond the Equation. And today we call this fault here the Universe Roundtable. I hope you guys don't mind. You can see the slides will be changing, but here we try to capture different essence of our universe. The atom, LHC is over there. You have the black hole that I get from Interstellar. Since our previous guest was Dr. Kip Thorne, he was the inaugural speaker in this podcast. And James Webb Space Telescope over there, and some simulation of the world was over there. So try to capture all the essence of it. So right now, since we have different speakers from different areas of expertise, we would like to gain that by navigating through the universe history. And in beginning, I will say, call this time zero. Of course, there is no time zero. But since we added our imagination right now, we don't know anything in the beginning. Basically, we don't know, we call it singularity because our equation doesn't work. It diverges, we don't know how to make it work, and we're hope for a new theory to solve that problem. But what we know that we have what we call the blank epoch, where we can work after that, not at particularly blank epoch with temperature 10 to power 32, energy 10 to power 29, and the time was 10 to minus 43. And here the question will be, I think, for the guys that doing gravitational field over here, how guys you get information about the early universe? I think what tools you guys use to know about that?
Yeah. I guess I could start with that.
This one, please. Yeah.
So, you hear me on both? Or
Yes,
does it matter?
this would
Yeah. So when I was in graduate school, I was working at Penn State. I was in the Center for Gravitational Physics and Geometry, and we were actually speaking of Kip Thorne. We were basically working on the same thing with LIGO, and I was working on the numerical relativity part where we were modeling the gravitational wave sources for LIGO. So actually, first time I met Kip Thorne was when I was in graduate school and I was working on a LIGO project.
Wow.
And got to go out to Caltech and brief him on my research. So there was other people in the center who were working on things like quantum gravity. And those are people like Lee Smolin and Abai Ashtekar and just there's several people who were doing that kind of work. And this is the kind of question that they were asking about when you get down to this Planck scale, what's going on in terms of gravity. And it's still pretty much an unanswered question because, it's never been a fully accepted, realized this is what's going on at that level. There was questions about the transition to the Planck scale. And actually, one thing that happened recently was Roger Penrose, who also was at that center. He basically came out and said, I think we're on the wrong track. Maybe there isn't a quantum gravity. Maybe it's just classical, and that there's just an interaction between quantum fields and a classical gravitational system. So there's been kind of a thinking in that direction, but so there's a real and then there's other people who came up with this idea of what they call the F of R theories, where it essentially, when Einstein came out with his theory of relativity, he had his biggest blunder where he added the cosmological constant. And, and later on he said, well, the reason why the cosmological constant wasn't there initially was because you could get the relativity equations to work without putting it in there in terms of a workable gravitational theory. He added that in there to get a static universe, which of course didn't work anyway. But the reason why it works is because when you look at both sides of the Einstein's equations, if you take the second derivative or the Laplacian of it, of both sides, you get zero. So it's basically saying that the divergence of this thing is zero of both the left and the right hand side, so it works. Well, if you take this same divergence, or what we call the conformal derivative of the metric, term, which is the little g in the equation, it also goes to zero. So if you multiply it by any constant, it still works and you got zero. So the f of r theories, they basically work by adding in these extra terms that depend on curvature. But when you take this conformal derivative or this divergence, it still goes to zero. So you can add these infinite number of terms and still get the equations to work and yield, and still, because it's still going to come out as zero. So, and you need that because you want conservation of energy and all this other stuff to work. Well, when you start putting in these extra terms and you start looking at what it does to gravity, what happens is you can start modifying gravity in such a way that you get something that looks like inflation, which is inevitable. And you could start probing the universe at tiny, tiny scales where you could see that these things work. So there's all kind of different ways that people have gone about trying to figure out what's going on there. The only thing we know for sure is that if you actually got to a singularity, you don't have time, so that literally would be time zero. And you don't really know 100% what's going on with the gravity.
But that's take me to since we talk about space-time and we talk about all the great minds behind the universe expansion or the gravitational waves, I will take you guys a little bit back in time, and maybe when I read about the Big Bang model, which is not theory but the model, and how it come to life and the history behind it and how the word Big Bang come from Fred Hoyle. I think that was in the BBC when they asked him about the new model by George Lemaitre, and he said it's like a Big Bang. So it's like very unique sound, and from there it's become a Big Bang. So I would like to ask Victor if he would like to tell us what's the Big Bang means. Is it really the beginning of the universe? Is it an expansion? Why are we too attached to that model?
In reality, every question that has been asked about the Big Bang in terms of what we see now, because that's all we can do, right? We cannot go back there to the singularity, right? We can go as far back as before reorganization, and then we don't see any longer. But the point is, based on what we see now, when we test the Big Bang theory, it works.
Which is what the Big Bang theory? What you guys?
Well, is the idea that you start tiny, you have a lot of energy that according to M, E is equal to MC squared, you can turn into mass, okay? Instability, that's how physicists love to explain the stuff that we don't understand. There was an instability, okay?
It's one way.
Okay, yeah, well, there's instability. We can talk about different kinds of instability, but there was an instability, okay? And then this energy, it's creates the universe in terms that the clock starts at that point, time equals zero, okay? At whatever temperature it was, space is created because now it's expanding, right? So now you have the creation of time and you have the creation of space, okay? Based on allowing that instability to grow, okay? And the instability to keep on growing in terms of producing this thing, right? Because you can have instabilities that vibrate and move and whatever, don't cause long-term effects. This one did, right? Okay. So, but the point is that if we think I think you mentioned it before, when you look at the expansion of the universe, a simple expansion of the universe, we find that the age of the universe and the expansion of the universe don't match. The size of the universe, okay, and what we believe the age of the universe is, well, wait a minute, the universe is way bigger than the time we calculate. And that's the need to go back and look at that instability and say, maybe, okay, something happened.
Inflation.
Correct, right? And you throw inflation in, okay, you do the math again, you work with the equations, and now suddenly, I can actually match now. Okay, the age with the size of the universe if, okay, that particular period of time was this way, the other way, lasted this long, right? So suddenly, what you were explaining to the young lady to match your initial condition
Yeah.
to what we see now, then you can actually explain what happened in there, what we believe happened in there, because then we can get from there to there, right? And in many ways, that's how science, actually goes, right? I mean, all we can do is measure now.
That's good. And since the universe started, somehow, we're here now. And right after the blank epoch, we have the ground unified. And when we think, okay, all the forces was one force, that's what we think. Everything was combined, and then they start to split. And this is where particle physics comes into the game. So we have we have the weak nuclear force, we have the electromagnetism, the strong nuclear force. And you guys said that the standard model is supposed to explain them, not purifying them, but at least explaining all the three forces, not including gravity. So can we, in simple word, what's the standard model?
Well, okay, the standard model is, there is a standard model of particle physics. That's the one we are talking about.
That's what we see here.
Yeah, that's right. It's an attempt to make sense of the collection of the particles that people were discovering at the beginning of the 19th centuries and so forth. We know that the electron was, first there was the X-rays of, it's called X-ray. Nobody understood what it was, and it was called X. And then electrons, and then people understood the neutrons and the photons. In fact, there were some physicists who at that point believed that physics was over, or was going to be over
at some point.
in 6 months. But then things didn't turn out that way. Many other particles were discovered, and when the muon was discovered, some physicists claimed, who ordered that? Because many things were being discovered. So the question becomes, how do we make sense of all of these things and understand them? And the first attempt at unifying forces was really Maxwell's
equations.
Magnetism, right? That's the unification of electricity and magnetism, which we learned separately before we get to Maxwell's equation, and see that in these four equations, you can explain these two.
No, the same one, but just get closer.
It's fine, yeah? This one is okay. Should be okay.
Now it works.
Yeah, so that was the first attempt, and so to fast forward, the standard model is really trying to make sense of all of these particles that we have and all of the forces that people have come up with. And I think it's a remarkable theoretical achievement that certainly rested on a lot of experimental observation also, right? It's, I go back, we talk about the discovery of X-rays, and then you go to Planck with the black body radiation explanation, which is remarkable, that triggers, quantum mechanics, essentially, right? And so the list goes on in remarkable insights, both theoretical and experimental. When Dirac proposed, for example, the
particles, antiparticles,
equation which essentially tell us that there is antimatter, right? Yeah. So you have all of these series of things over the years. How do we understand them? And that's what that was the questions when you get to quantum electrodynamics and go beyond, and now you're trying to understand the quark model, essentially. Yeah. So that's where the electro weak, when electromagnetism was already unified, and then people understood radioactivity as nuclear force, but a weak version of it. And how does that get unified? Then you begin at the beginning of the universe, was there one force? And how did they get to become four that we have now? And electroweak, the standard model, which is essentially first explaining the spectrum of the particles that we have and how their masses can be explained, is by itself achievement.
One of the most interesting thing I heard when I was just still an undergraduate is that the universe in the beginning was chiral symmetry. And I don't know what chiral symmetry is at that time, but I like the term. And then to explain it, the professor said that nothing had to carry a mass. But you guys telling us that the electrons had mass. Even the neutrinos still have mass. People get Nobel Prize for that. But what's mean that in the early universe, everything was massless, or supposed to be?
In the evolution of the universe, when you see the chart, at some point, particles get mass, and that by interacting with what we know today as the Higgs field, right? Which essentially the couplings of that interaction with the Higgs fields generate the mass for these elementary particles. That's how we know them. Yeah, and without the mass, we know that particle physics equations don't work. And,
Exactly.
They came up with the beautiful theories, didn't have the mass in there, but all of these particles, they have masses. And then people didn't understand why the masses were so different when you go from the electrons and you talk about all of the fermions and so forth.
Yeah.
And, that mass spectrum, why are they like that? Nobody understood what it was until the proposal of the Higgs mechanism to explain the mass. But today we know that mechanism only explains a fraction of the masses. Actually, there's the gluon dynamics. That's, if you take the proton's mass, it's not explained fully by the Higgs mechanism. You need some other dynamics, which today we know, or we postulate to be the gluon dynamics, which I think you're going to tell us at the EIC.
Yeah, well, so at least the Higgs mechanism, as you said, does explain why the particles get their mass, but there's no explanation for why those masses are those exact values. So that's a big open question. There's still many big open questions. And then, for the gluon dynamics, that actually turns out to be it turns out that an up quark, right, is only like 5 MeV in mass.
Very small.
And the, gluon or proton, which is made up of 3 quarks, 2 up, 1 down, is more like, 982 MeV or close to a GeV. So it's only like some 5% of the mass comes from the raw mass. The rest comes from the gluon dynamics. Yeah. So, and that's just because the gluons, it's E equals MC squared, right? So the fact that, energy can be mass, right? So all of that exchange of energy still, affects gravity, because the stress energy tensor doesn't care about whether it's mass or
equivalent
energy. It's equivalent. Yeah. So that's what explains actually most of the mass that we observe and can detect, right?
So combination between the Higgs mechanism and the gluon.
And the QCD gluon dynamics. Yeah. So internal, energy there's so much energy in QCD, right? So that the fact that if you try to pull apart these quarks because of this confinement property of QCD, because it's non-abelian, you can actually create particles out of nothing, right? If you can pull them out far enough. And we do that all the time. We don't pull them apart, but in these particle colliders, right, we smash them so hard that they bang into each other, at that level, kind of really like billiard balls, since we're colliding elementary particles that, with no substructure. They can shoot off so hard that you really are pulling them apart, and then in the vacuum in between them, you pop particles out of vacuum that, particle-antiparticle pairs, creating matter out of the energy created in the wake of that.
You guys
so that's just an example to show you how strong QCD is.
You move to the next step, which I was going to anyway, because we get the particle created, the elementary particle, fundamental particles. Fundamental particles have been created, and now the universe in very, very extreme high temperature. And we get nuclear physicists to tell us, we created the universal soup. And I was writing one of the, I will say it's sort of public audience new magazine that's for the American Physical Society. That was about the new Atlas discovery for the top quark in the QGB. And I wrote that article, but we tried to find a title to it. and the title was "The Primordial Soup of the Universe Was Full of Flavors." So, what's this primordial soup of the universe? It's part of the high energy nuclear physics. What does that make?
Yeah, so that's essentially. I just said that these elementary particles, like the quarks and gluons, are confined in protons and neutrons, and then those then bind together into nuclei. But if you really get hot enough, or get to a region where the universe was hot enough, you would essentially melt those so that the independent quarks and gluons have enough energy that they're not bound. They're stronger than the quantum chromodynamic attractive force, and so you can actually melt them into its primordial quark and gluon selves, and not these composite particles that aren't the fundamental elementary particles.
And why are you guys so interested about that?
Huh?
Why are you guys so interested about that?
It's what the universe was, was, right? So if you're interested in where we came from and how the universe, evolved, you have to understand all of the epochs, which is why we ask about the Planck scale, right? So we believe we have most of the physics up to the Planck scale, except for dark matter, dark energy. So, but
that's good. But see, you guys talked about the AIC, you and Kitavi, and since we have gravity too, I attended this lecture by Jean Lejeune when he was talking about the AIC and the AC future. But he described the gluonic interaction that we expect at AIC as two gluons hitting the protons simultaneously, or this is what he explained at least. And he said that this could be close to a graviton interaction, sort of, mimicking. Each one is spin 1, both are spin 2.
yeah.
So it's like making a spin 2 interaction. So it's not actually quantum gravity, but it's close. Can we say that?
I think that you can get situations where mathematically the equations that describe one situation is analogous to another, right? So then in that kind of case here, you need some spin 2 object, and you can create that in these interactions at the EIC. So it isn't that you're creating a graviton, but you're creating a mathematically analogous situation, and therefore understanding how that behaves will let you understand how a graviton would actually
So what we can get from that at least the interaction is possible in nature.
Yeah. And why do we want to do this is because you can't actually manipulate a graviton at this moment, right? So
Exactly.
You try to find out you just become clever and try to find an alternative experimental technique, right? That is similar.
That was very interesting. When I heard about it, I have a friend, he's a string theorist. So I went to him and I told him the idea, what do you think? And he said, similar. He said, to the first order, they are very equivalent. So if you guys can confirm that this happens, so we know that this is possibility of nature, we can find the graviton in some way. But that actually takes me back, okay, the universe now is expanding. And we had recent discussion about what we call the Hubble constant tension. I think our general relativity people knows about that. So how many times did the universe accelerate and deaccelerate? Who's riding that car exactly? What's happening there? But can we say what is it first?
The Hubble tension?
Yes.
Okay, so the idea here is that when you look out at the universe, you can see that the rate the universe is expanding is proportional to how far away you're looking. So if you look at a galaxy that's close to us, it's not moving as far away, as fast as one that's really far away. However, this is not perfect. It's like somehow there's spots where it doesn't quite work right. And so you look far away and you see something that's moving really fast, and you look closer and you see something that isn't exactly doing what you think it should. And then there's other parts that are the same distance that are doing what they're, moving away like they should be. So the question is, kind of what's going on? Why are these different parts of the universe behaving differently? And that's still kind of an open question, but it seems to be it comes from the fact that there's just a non-uniformity in the universe, and they don't know if maybe it has something to do with dark matter or dark energy in different places, or the distribution of them. Somebody mentioned a rotating universe, And
Wow,
I think
okay.
that there was some aspects of it were even tied to that. And so it's a pretty good unsolved question because the Hubble parameter is more like an average
Yeah.
than an exact thing. And when you're talking about a universe and you're talking about this big universe, it's expanding and we know it's expanding, it feels like there should be a better answer than, it just averages out to that.
Can I give you a better answer?
Yes.
Okay, so we have the Department of Physics chair. He's gonna give his answer right
Yeah, I'm going to go to astronomy.
now. Okay. But use the mic, please.
Okay, something we love in physics or chemistry, something we love in science is simplicity. We always tend to think that the simple answer, okay, must be the right one, right? When things get too complex and too convoluted, we're going the wrong way. Do we agree?
Occam razor, close enough.
Oh, fair enough.
Yeah.
Now imagine, let's go back for a moment because the way we get those velocities, okay, is that, okay, I can look at faraway galaxies. Okay, we look for supernova type ones. Okay, they're very bright. We can see them from this distance. We know the luminosity, and because we know the luminosity, we can get the distance. Okay, now supernova type ones need to be, the light we see from them needs to be calibrated, properly calibrated.
Okay.
Okay, so I see a galaxy very far away. I see another one much further away. I use supernova type ones. I get the distances, and based on a model that will say that they're expanding linearly, I should see something. And what we find is that no, we're not seeing what we're expecting.
Okay.
Suddenly, it must be that they are accelerating. So it's not my idea. Somebody, an astronomer, came and said, an expert in supernova type ones came and said, we still have some problem with the calibration of the light of supernova type ones, right? So we can see it far away and we're saying it's this luminous, but there's a delta to that luminosity, right? And if that delta is large enough, when you calculate the velocity, okay, it's not linear, it's different. The next value is different. So you're saying, oh, wait a minute, it's not a linear growth. Acceleration must be happening because it seems to be moving faster. If that's a big if we found out that it's an issue with calibration of the light curve of the supernova type 1, and we could correct that, the question is, do we still need dark energy to explain that, or suddenly the acceleration goes away because we had a problem with the light curve calibration from the beginning?
But I'm going to point out.
I'm just playing devil's advocate.
Okay. Well, I'm going to point out that we have other things besides the supernova now. We have, instead of the supernova, they call them standard candles because they're all basically the same, or at least we think they are. We now have standard sirens as well because of gravitational waves. And the idea that you see, ever since 2015, you saw the first gravitational wave collision of two supermassive, or two black holes, intermediate mass black holes. Since then, they've detected.
There's one there.
Yeah, there's one there. Since then, they've detected, I think, hundreds more of these things, and so they have a lot of data they're working with, and they're all far away, and they're all within the visible universe, and so they form standard sirens because we know some of the physics of them. We know they're all redshifted, just like the supernova. But I think that we're also seeing the Hubble tension with those as well. So it may not be a calibration thing, or it may be, or if it is, it's a common calibration thing that we're seeing with the redshifting.
The article I read back when I get the idea or not about it, they always try to differentiate between two kinds of measurements. One of them coming from the telescopes for the expanding galaxies, and the other one was coming from the cosmic microwave background radiation. And the two values for the Hubble constant doesn't add together. And then when we get a third measurement, it was in between. And then they didn't match. And I think now we're a debate happening right now if James Webb Space Telescope can provide us with more shrinking error bars to solve that problem. But since it's a problem that's going to be there, which will take me to my next step in this in this broadcast. So in the current days, now I want to switch again to the particle accelerator guys when they're too many accelerators happening currently, or too many physics of accelerator. So what you guys hope to achieve next at the LHC, first we heard about the supersymmetry particles, and we don't know where they are, but
What?
the supersymmetry particles, where that stands, and what's the coming at the LHC.
So we are in the process of doing upgrades of both the
Great.
accelerator and the detectors,
Of course.
and that's going to be the high luminosity LHC, which in the next few years should be ready to start operating. Currently, we are still taking some data in the current run phase. We hope that there will be some discoveries coming up. So we have discovered the Higgs boson, and that's the main thing that has come out of the LHC operation. And then there's a lot of measurements that have been made, very precision measurements, and consistent with the standard model in many cases, although there are some small deviation which suggests that there may be new physics, but we still don't know the direction. There was a lot of interest in supersymmetry before, but we haven't found it, unfortunately. So that interest has cooled down. It may still be there. It may just be that we have not explored the phase space, or our detectors have not been sensitive to the area of the phase space where supersymmetry should exist. But the fact that we haven't found it is really discouraging. It was a brilliant idea. You even try to explain the merging of the couplings at some point, which will have, which all suggests that he was on the right track theoretically, but unfortunately it hasn't panned out. Then other paradigms came out, like things like dark sector states and so forth, to explain a bunch of things, including the muon G-2 tension. Unfortunately, we haven't found any dark sector states. A few excesses have popped up here and there, but we still need more data to see whether any of these things leads to new physics or not. And that's why the high luminosity LHC is actually being prepared.
So the upgrade will be on the luminosity side and the energy
On the detector as well.
detector aspect.
Yeah,
So
both of them. Both the accelerator is being upgraded, and also the detectors are also being upgraded.
Okay, that's great news.
And then people are discussing way beyond the high luminosity LHC, and that is now is really a debate of what should be the next phases of colliders at that point. And many, depending on who you talk to, you will have different answers. So I won't speculate.
But it's interesting, no? We as physicists are always, there's always more data, right? I mean, we always want.
Yeah, please.
There's this need for data, and no matter where we are and what instrument we're using, okay, the conclusion is yes, we got some more information, we got perhaps one or two more pieces of the puzzle, we kind of starting to get a glimpse of what's going on, but we need more data. Okay, no, I'm not. That's no criticism. I mean, that's absolutely true for astrophysics too, right? I mean, we have models, we have ideas, things seem to work in a particular way. A little more data will tell us if it's really going that way or the other, and we move forward always with the hope that the next instrument that perhaps nobody has come up with, what's going to look like or what's going to be, but we know that it needs to provide this kind of data so we can actually tell if it's going that way or the other way, or maybe we were just wrong all about it. No. We need to step back, right?
I was about to complain about that part, but you covered it. Don't give it away late. So when you say more data means quantity and
quality.
Quality, and quality here mean different detectors as Katavi was saying, that will cover different range. So when we say more data, some people say, okay, you guys want to increase your data by a factor of 2.5. Not always. Covering a different phase space, which might need a different machine, is also more data. So more data is a general term for many things we're doing.
I think we always feel comfortable or more comfortable when, okay, I got this wonderful result using this technology, using this whatever, and somebody over there using a different instrumentation came to the same. So now you have, wow, right? I mean, it's awesome that from two different perspectives, we got the same kind of data or observations that we can say, hey, I mean, it's not only my experiment, it's not biased one way or the other. We have information that collaborates each other from different backgrounds, different technology, whatever it's going to be. And that gives a certain feeling that, yeah, we're going in the right direction, right? I mean, we're moving, we don't have all the answers. And that's kind of nice because we keep our jobs, right? Okay. I mean, if we answer all the questions, then what would you need physicists for? Okay. But something that takes all this stuff and merges it together or sews it together in a way that makes a pattern is that you get discoveries from different places, coming from different theories, perhaps different technologies that match. And that is amazing all on itself and give us the confidence that we are moving in the right direction, no?
That's good. Actually, to Mickey, what's your expectation for the end of REC? So this year we have the final run at REC. You like it or not, that's what's going to happen. We're moving to AIC. So I would like to get you and Katavi perspective on the final run at REC and the beginning of AIC.
I'm going to start by crying.
Oh.
Yeah. No, I've been working at RIC since the very beginning, actually. So I started as a grad student at RIC, and I guess I'll see it end as well. So it's been 25 years. And over those years, I mean, I actually, like we were saying, you take the data, right? And where we take data is actually usually where no one's ever looked. So that's creating a microwave radio telescope, putting it out, a microwave telescope, looking out in space, or in our case, colliding nuclei at the highest energies ever at the time. And there were questions like whether, the phase transition, QCD phase transition was, going to be first order, even second order, right? Or turned out to be maybe the least interesting a result, but that's just what nature is, right? We wanted to find the answer, and we found it. I believe, anyway, that it was a smooth crossover. You basically get this very hot quark-gluon plasma, and as it hadronizes, just kind of smoothly transitions without this latent. There's
no any discontinuity.
Yeah, there's no discontinuity. But it was really beautiful the way the data came out because we saw that it could happen. It happened that way, right? So you could see the quarks flowing out, and then if you looked, we only see the hadrons, but the pattern of the hadrons as they flew out, as they came flowing out, followed exactly what you would expect from quarks flowing out smoothly. So I think it all kind of like gave us the right answer. And so there's still lots of other things that even from the earliest days are still open questions like chirosymmetry, restoration. So one of the big motivations for RIC was we would restore this broken symmetry, chirosymmetry, and then when that happens, you'll see the masses that we've always measured, like the phi, will shift, and so people have found shifts, but there are other reasons that there might be these shifts. So there's always this argument, just like the Hubble tension, that there's other reasons that may be more mundane, and so we've taken this data and actually. I think we'll be analyzing this data for the next 5, 10 years, or maybe even longer, because what will happen is some, young hotshot theorists will come along with a different idea that like really proves that this is, chirosymmetry restoration if we just look at it in this particular way. So for the end, we have lots of things. So this is marked as, the year we're going to take all of the data that we ever want, and we're going to close out the science program. I think that's partly political because we have to have a way to say we're going to finish it. But yeah, we're going to take the largest data set ever. It'll be the highest luminosity with a new detector, at least in the S-Phoenix case, that will be able to take like orders of magnitude in some cases for many of the observables. And so in that case, we're seeing something different because we're taking much more data. So we'll be able to see much, lower signal to noise things and things like that. So, or very rare probes that you can't have produced enough of in the past that now we're going to get copious amounts of, like the Upsilon. And so we'll be able to, with the Upsilon, for instance, we'll be able to put another. So how do you measure the temperature of this quark-gluon plasma? You can't just stick a thermometer and it melts. And it's a tiny little thing anyway. So you have to create or think up probes that are sort of self probes. So Upsilon has a binding energy. It's a bottom anti-bottom quark pair that forms a meson. And so it has a binding energy that theorists can calculate. And so if the quark-gluon plasma is hot enough, then it can't form because it basically gets melted if it's above that binding energy. So we look to see if there's a modification, if we can see fewer upsilons coming out than expected because they will have been melted and so they wouldn't have been able to form. So things like that are what we're trying to get in this last data set.
So even if the detector stopped working, we have data to analyze for the several coming years.
Oh, and it's not just having taking the data. It's more people later on coming up with brand new ideas and being able to look at the data with a different perspective. This is why we try to get as many students as we can, because the more diversity of thought, the better I think we'll be able to.
That's what happened with me when I started my PhD. Some people think, okay, some measurements already done.
Yeah.
By repeating them, you might not add anything, but getting a fresh mind to look to the same data, you just come up with new ideas and you figure, okay, it's done, but there are several aspects that you need to look at and you learn from them.
Yeah.
And so let's hear also from Kitabi, his taken on the future of the particle physics before we go to the future of the gravitational physics.
I hope we find something. The direction of the fields really depends on really finding where to go, because right now there's a lot of ideas theoretically, a lot of work experimentally. Yesterday we were discussing that both nuclear and particle physics, they are not really physically separated. It's really one field continuously. So any input from the EIC will serve to shed some light on quantum electrodynamics and quantum chromodynamics, more quantum chromodynamics, and ultimately, the direction that we should take in particle physics. And if at the next phase, high luminosity LHC, we find a hint of something or evidence, that will also hopefully shed some light. The fact that SUSY has not panned out, brought many of these other things, including the dark sector states, and which also is now many years people have explored those things, and we didn't really find anything beyond the standard model. So we are hungry to discover something.
Hungry for knowledge all the time.
So, I can only hope that the detectors that we are preparing now, both at the EIC and at the LHC, and there are also some tabletop experiments that are really very good, that people are coming up with bright ideas for fixed targets or type of experiments, or even lower energies, or places like at Jefferson Lab or at SLAC and other places that are not the big colliders like at the LHC, but nevertheless they are trying to answer the same type of question, searching in different regime for new physics. Then we have our colleagues from the astrophysics doing direct detection experiments or indirect detection experiments. All of those things are the collective search of where to go next. And I hope somewhere in that collection of searches we'll be able to find a direction.
That's so good.
Of course, the big simulation that you are doing for us.
So actually, as we started with the gravity and the world expansion, we might come back. It's a fancy picture that you guys use for the cosmic microwave background radiation. I think it was blank. That's That's the telescope, Planck telescope. But now we are in the era when we have one of the largest telescope we ever have out in space. That's the James Webb Space Telescope. We have LIGO experiment, and Kip Thorne mentioned that they're already now building a new experiment currently try to detect the gravitational wave from the early universe. So I would like to take your point of view, you and Victor, on the what you guys expect in the future of the gravitational physics and astrophysics.
Yeah, and I think I'm probably going to echo some of the things Kip Thorne said, but the idea has always been, ultimately, with gravitational physics, was to do astronomy. You know, it's like we go full circle here. And the point is that in the beginning, the hope was just to detect a gravitational wave. And in numerical relativity, what we were trying to do is we were trying to model the gravitational waves from colliding black holes, because to give them something to look for. And they used artificial intelligence before anybody knew what it was to be able to look at all these different data sets coming in, to be able to pull out the data of when they actually had colliding black holes. And now they're working on even more precise gravitational wave detectors and interferometers. There was been a plan for a space-based one for years called LISA, and there was more accurate ones that were going to be built on Earth, and they were going to be able to look at different frequencies. So instead of just looking at something on the order of 100 hertz to a kilohertz, they were going to be able to go all the way down into the nanohertz range, and with the space-based, and they were going to go down. Actually, sorry, the millihertz range for the space-based, and then the nanohertz range with something they call pulsar timing, where they're using radio astronomy to actually detect gravitational waves on a long baseline. And the idea of all this is that eventually they're going to get so good at detecting all these gravitational waves that they won't be limited to the stuff that we've modeled, and they'll actually be able to detect new things, and they'll be able to do very precise measurements, and they'll be able to, learn about the process of supermassive black holes colliding, or see the dynamics of what's going on the surface of a neutron star, or be able to see things that we couldn't even imagine right now, but they'll see that there's a gravitational wave coming from it, and then they'll probably have, at some point, the experiment gets ahead of the theory, and they'll be like, what is this we're seeing? And we'll just have to figure that out. So I think that's always been the hope. And in the meantime, I mean, they've detected things like we've already seen that there's evidence of background gravitational waves. And that's one of the things that I was looking at in my research, is that, I always figured that there would be something like that, but we don't know the characteristics of it. We don't know if it's coming from the early universe, from cosmology, or if it's just the background of many, many gravitational wave collisions between black holes going on that are just kind of overlapping stochastically. So there's a lot out there to discover. We don't know what we're going to see, and we don't necessarily even know all the technology that's going to be involved in it.
Great. Victor, go on.
One of the biggest discoveries from Galileo, let's go back in time. One of the biggest discoveries from Galileo was that, astronomers were eyeballers, right?
Yeah.
I see. Okay, look at that, right? Look, it's moving, okay, etc. Right? And when they see all the stars, okay, and some brighter, some dimmer, some look bigger, some look bluer, all these kind of things, okay, there are patches of sky where obviously there are no stars. Look, there's a black patch right there. That I put my eyes on it. Mickey, you put your eyes on it too. He has better eyes than I do, and both of us see nothingness. He grabs his little wimpy 1-inch telescope. He points at that black patch where his eyes and his mind are already telling him there is nothing. And when he looks, there are tens of stars in that little patch. I can almost imagine him putting a telescope down, rubbing his eyes, and doing it again just to make sure, because, maybe my eyes are irritated. I've been looking for a long time. So he looks, and then he starts looking for patches of sky. I mean, that alone really rocked the foundation of science and to some degree of religion of the time in terms of that, well, we're not seeing everything, for crying out loud. There's a lot more to see, right? So the next telescope, a Newton with a bigger telescope, sees better, right? And again, goes to those patches and you see many
More
stars.
details, yeah.
Right? So correct. So suddenly the again, more pieces of the puzzle are coming together because we see better, we see more, right? So starting from there, the new instrumentation, the concept that, and to some degree, the hope, if not faith, that we're gonna see. One of these instruments is gonna be able to see what we're missing and we'll be able to put it together, correct? I mean, we feel the same way. And somehow from that end and from this end, are we going in the same direction, right? I mean, we come to the point where we're looking for the same things, okay? If there is gravitational energy, we should be able to see some effect, the way you're coming from it, the way we are approaching it, and the same for dark matter, right? These gravitational waves, okay, for the theorists, I mean, it means that there's hope that actually, okay, the four forces we know today may come together, right? I mean, if you could find a graviton or something like that, then gee, everything will come together in a beautiful way, right? Because waves and particles, right? And it's just different sides of the same coin. And a lot of theory will come together. And more importantly, will open the doors to, we never thought that things were going to be this way or the other way, right? I mean, there's always that, we never knew. We didn't even guess that it was this way or the other way, right? And so we're all expecting for that.
Agree.
Okay, so from the astrophysics perspective and nuclear and particle physics perspective, we can sit at the table now and discuss things that at some point way back, there's no connection. What you're talking about is over there, what I'm talking about is over here. And now suddenly, well, we see the connections in what we're talking about, right?
That was the point, yeah.
And thank you, correct.
Oh.
That was the point.
So with that, can I prove that now? So actually, with the answers from you guys to the last question, that bring me to the conclusion of the Beyond the Equation, the Universe Roundtable. And again, guys, we try to tell you, as Victor was saying, physics is connected from the biggest galaxy to the tiniest particle you can imagine, from things that the astro guys are looking at the beginning of the universe to what's our particle physics friends are looking at to the tiniest particle. Everything is connected. And again, I will say, stay tuned for our next part from Beyond the Equation. That's the podcast founded by the Department of Physics at Texas Southern University. Thank you. Thank you, guys. Can we take...